And now for our last talk, we're going to switch gears and move online, as well as switch gears scientifically. And Nicholas Vieira from McGill is going to talk about a possible neutron-star black hole merger.
All right, cool. Can everyone see my screen?
Yes, we can.
Okay, great. So hi, folks. My name is Nick Vieira, and I'm a PhD student here at the McGill Space Institute under the supervision of Professors Daryl Haggard and John Runn. And today I'm going to talk about our work in search of an electromagnetic counterpart to a potential neutron-star black hole merger detected via gravitational waves with CFHT. So I'm going to start off by talking about neutron-star black hole mergers in general and the emission they produce. I'll then describe our program and the constraints we're able to put on the event. And then I'll talk about the future of gravitational waves in CFHT. Before starting, rather than a simple land acknowledgement, I want to quickly reflect on the relationship between Indigenous folks and astronomers. So to start off, I'll note that I'm coming to you from Tiohtià:ke, otherwise known as Montreal in so-called Canada. And something which is increasingly, I think, concerning to me from this place is this perspective that when it comes to certain projects, astronomers have a lot of trouble taking no for an answer, and I think we need to be prepared maybe to do this going forward. I think there's a strong lack of trust in many communities, and for good reason. Here in so-called Canada on the west coast, the Wet'suwet'en have been fighting for the last 3 years to prevent the Coastal GasLink pipeline from being rammed through their unceded territory, but this hasn't stopped the RCMP from using excessive force and violence to try and intimidate land and water protectors. And as we know with pipelines, it's not a question of if they spill, but when. In Oahu, the water has been completely poisoned due to the negligence of the Navy. And so these issues of really abhorrent, unchecked colonialism are connected. And as astronomers, we're not exempt from this. And I think similar issues are playing out all over the world. And so I think we want to take a step back and make sure that astronomers, as astronomers, we're not a part of this colonialism, and determine if this is a relationship that can be repaired, and if not, if we need to take no for an answer when it comes to certain projects. Getting back to the science though, so as I mentioned, I'm going to talk today about mergers. And so neutron-star and neutron-star black hole mergers are one of the primary targets of the LIGO and Virgo gravitational wave observatories. However, these events are also incredibly rich in the electromagnetic spectrum, which I think is communicated well in this cartoon. But what I'm most interested in is the kilonova, which shines bright in the ultraviolet, optical, and infrared on timescales of about hours to about a week. And so that's what I've highlighted here. And a kilonova is an example of a radioactively powered transient event. And what I mean by that is that in the exceptionally neutron-rich ejecta, which follows these mergers, radioactive isotopes of heavy elements are rapidly synthesized via rapid neutron capture, otherwise known as the R process. These isotopes decay, and their decay products then thermalize, producing the transient. And crudely, these mergers can have 2 or more dynamical components with different colors due to their composition. So you expect something like a red component, which is thought to be caused by the large opacity, some of the heaviest elements, especially the lanthanides and actinides, and then a bluer component, which should originate from lighter elements with smaller opacities. But we saw a kilonova a few years ago. We saw a neutron-star merger back in 2017. So why should we care about another one? Well, we think that neutron-star black hole mergers in particular may produce redder kilonovae. And this has important implications for the astrophysical site of the heavy R process, which is still under debate. It's not clear if neutron-star mergers alone can produce the heaviest elements in the universe. And aside from the cosmic nucleosynthesis interest, detecting a neutron-star black hole merger in gravitational waves and electromagnetics, so multi-messenger, can be really, really useful for understanding the neutron-star equation of state and also pinning down the value of the Hubble constant. And then finally, and maybe most excitingly, we've never seen a neutron-star black hole merger. We want to tick off that box and say that we've seen one. So when GW190814 was detected by LIGO and Virgo in August 2019, a public alert was sent out, and within minutes of the event, we jumped on it. So here you're seeing a sky map of the source, where it came from in the sky, as well as an estimate of the distance to the source. And at the time, this event was the first candidate neutron-star black hole merger ever detected. It also had an extremely small chance of being a false alarm, absurdly small, with a false alarm rate of 1 in 10 to the 25 years. And finally, had a really excellent localization on the sky. The little hand that I have in the bottom right is there to guide your eye to the part of the sky where the event most likely occurred, which is so small that it's almost invisible. So in light of all of this, as I mentioned, we almost immediately jumped on the source of the CFHT. And our program at the time was to use either WeirCam or MegaCam on CFHT as available. In this case, we used MegaCam, which was on the telescope, which of course does a really great job of acquiring deep images of large chunks of the sky at once. So it was incredibly suited to searching a large patch of the sky to try and find a counterpart to the gravitational waves. Here you can see exactly where we acquired images in the sort of main lobe of the localization region, the region with the highest probability. And our observing strategy was a hybrid of two strategies. So we tried to image as much of the 50% region as possible. So that's the region bounded by the cyan contour. And then we targeted galaxies with high luminosity in the outer parts of the 90% region. So that's the region bounded by the dark blue contour. We also began our observations at shorter wavelengths in the G band, then moved to the longer in the Z, based on the reddening of the 72817 kilonova a few years ago, and the robust predictions of kilonova theory, which predict the reddening. We were far from the only folks to look at this thing. And so in a span of just a couple weeks, more than 100 candidates were detected, as you can see here. The most compelling of these sources were followed up upon, and in almost all cases, it was possible to sort of discard them for one reason or another, spectroscopic or photometric classification. But how do we find these things in the first place? As we use something called image differencing. And so that is what we did using our CFHT images. So what I mean by image differencing is this process of acquiring some reference image, which was taken long enough before or after the event, aligning that image with your data. So in our case, our CFHT images, matching the PSF and the photometry, and then subtracting. So here's an example where we've got a science image from MegaCam, a reference image, and then we subtract to get a difference image. And what we're seeing here is actually a known supernova, AT2019 NXE. There are a few problems or sort of pitfalls with this method. Firstly, image differencing can be really messy. So here we see two sources which might fool us when they are in fact the result of poor image alignment on the left and a cosmic ray hitting the detector on the right. And this introduces another problem where we end up with something like 20,000 potential transients in all of our data, which is far too many to visually inspect all of them. And that's, you know, the result of only about a week of following up on this source night by night. And so you can imagine that this problem gets worse with more observations. And so our solution to this problem was to use machine learning to classify the images. And this was very helpful. It cut down on the number of sources that we had to visually inspect by over 90%, which made this problem more manageable. I'm happy to talk more about our machine learning model later if folks have questions, but to summarize, we did not detect any counterparts, nor did any other team. And this has a few interesting implications. First, it could be that the lighter object in the merger was tidally disrupted within the innermost stable circular orbit of the larger, or that the lighter object in fact belongs to a new class of never before seen low mass black holes. However, this isn't the end of the story. We can use our non-detections to impose constraints on the event. And so that's what we did, comparing our observations to a really simple 1D analytic model for a kilonova. So here are our MegaCam observations, which we can interpret as upper limits summarized in the form of a light curve in the G and I band. And we include in this figure the best fit model light curves for the GW190814 NeutronStar merger in the G and I bands scaled to the distance of 190814. And we can see right away that we most likely would have seen a 17817 light kilonova at this distance, thanks to the really impressive depth achieved by CFHT. More generally, though, we can write down our simple analytic model for a light curve, which is mainly parametrized by the ejecta mass, velocity, and opacity. And then we can generate a suite of model light curves and see which of those light curves are ruled out by our observations. That is, which of these light curves which would have been detected in our images. And in this way, we can rule out different ejecta parameters. So here, we are fixing the opacity of our model and seeing which parts of mass and velocity parameter space are ruled out by our observations. So on the left, we fixed the opacity to that of a very blue kilonova, and on the right, that of a redder kilonova. And what you can see right away is that we can rule out a large fraction of the relevant parameter space, just with this simple model, thanks to our very deep images. We can flip this around and similarly fix the ejecta velocity, and then look at constraints in mass and opacity space. And we see that once again, we can rule out a large fraction of the relevant parameter space with our really simple model. Of course, as some of you probably know about this event, the LIGO-Virgo collaboration has since released the more precise masses of the objects involved. This was not known at the time of our program. But now we know that the heavier object was about 23 solar masses, the lighter 2.6. And in this situation, even if the lighter object is a neutron star, it would have definitely been disrupted within the innermost stable circular orbit of the black hole due to the asymmetric mass ratio. And so we actually don't expect any electromagnetic emission, which explains our CFHT non-detection. Nonetheless, this is still a really exciting event because by definition, the lighter object in this merger is either the heaviest neutron star ever detected or the lightest black hole ever detected. And so this source is sort of driving the theorists crazy. It's challenging a lot of our models. Looking to the future, there are a lot more exciting events to come. So here we're seeing the cumulative number of gravitational wave detections as a function of volume time, which is a funny parameter which takes into account both observing time and the expanding detection horizon of the observatories as they upgrade their sensitivity and carry out more observations. And speaking about detection horizons, we can look at this image here, which shows us how the detection horizon will be expanded in the next observing run 404, which is slated to begin at the end of this year. And you can see that the detection horizon for binary neutron star mergers is going to expand quite a bit, which is great because volume goes as distance cubed. So every little bit of distance out further that you can go is a huge increase in volume. And so we really appreciate that. And so we're expecting as many as 10 events to follow up on in 04, like the one that we followed up on in 2019. Lastly, in preparation for 04, I just want to shout out some of the work that a new student in our group, Nicole Ford, has been doing. So Nicole has been hard at work automating the process for selecting pointings with her new code, GW rank. And this code will be super useful. It's basically going to listen to gravitational wave alerts 24/7, ready to generate pointings at any time. And it generates these pointings as a function of instrument, filter, desired depth, available time, and the size of the localization region, which makes it really useful for MegaCam. And then alternatively, it can also do galaxy targeted observations where we look for galaxies with a lot of mass in them, which might be more appropriate for WeirCam, which is a little bit of a smaller field of view. And here, for example, is a just auto-generated set of pointings for GW190814 in the G-band. And it would have been great to have this back in 2019 because this took less than a minute to generate, which is much less than the few hours that we spent scrambling to do this back in August as we were trying to get our observations in the queue as fast as possible. So I think I'm low on time, so I'll just leave my conclusions up, but I am happy to take any questions. Thanks.
Great, thanks, Nick. We do have time for some questions. Any questions from the audience? Any questions online?
None so far.
No? Okay. Oh, we do have a question from the audience.
Hi, this is Lori Russo-Neppen speaking. I was wondering if many teams are coordinating the effort when you are trying to find the source and how this is working.
Yeah. So that is something that was not done as well in the past, but is getting better. So for example, there are tools like the gravitational wave treasure map where people can upload, as they're taking observations, they can upload their observations so that we don't duplicate efforts and waste resources. Also, I think there's a bit more communication between different teams so that one team can have observations at a really early epoch where you need mostly UV optical observations, and then observations at later epochs where you can use something like James Webb, which is a bit more suited to the infrared. So I think that there's a bit more communication between different teams, which is good. I think that that is the right way to do science, right? And that's the way that we'll hopefully learn the most about these events.
Are there any other questions? Yes.
A follow-up question. So what is the optimum in terms of a field of view and depth, if any optimum?
Yeah, so with an event like 190814, it was exceptionally localized. And so with something like CFHT Megacam, or also DECAM on down in Chile, those instruments are really good because you can tile most of the localization region really quickly. If you have a really large localization region, and sometimes these things can get pretty large, you know, hundreds of square degrees, no wide field imager is really going to be able to achieve the depth that you need. And so in that case, you want to turn to galaxy targeted observations where you basically say, more luminous galaxies should have more mass, more massive galaxies should have more stars means more binary systems, more binaries means more mergers. And so then you do a sort of galaxy targeted scheme. I think the optimum is both LIGO detectors and Virgo detect an event. It gets really well localized, and then something like CFHT Megacam can just scan the entire region to sufficient depth that we can be confident if we do or don't detect something.